GNS3, cancel. Okay, new project. Implement GRE over IPsec side-to-side VPNs. Use this topology. Routers iOS 15.2. Free routers. Switches. Layer 3 switches. I will use image IOU L2. Okay. And device. Between R2 and R1, gigabit 000. In my case, I will use gigabit 00 and gigabit 00. Between R2 and R3, gigabit 001 on R2 and gigabit 000 on R3. In my case, I will use gigabit 10 on R2 and gigabit 00 on R3. The connection to D1, gigabit 001 to gigabit 11 on D1. Okay, the same case on R3, gigabit 001 to gigabit 11 on D3. Gigabit, in this case, from 10 to 11 will be, in this case, I will use 11. 1011. And the connection to PC, gigabit 23, in this case 23. I would use gigabit 23. The connections to PCs. addressing table, cable the network, already done, basic settings, a command list for each device is listed below to perform initial configurations. Basic settings on R1, basic settings, interfaces and routing OSPF and static routes. Okay, this for R1. Okay, but this in my case is gigabit 00, only 00, and here 10, 10. And very good. Start R1. Configure terminal. Copy this, but enter to global configuration mode. Global configuration mode. Right click to paste. Okay, again. Right click to paste. Very good. Now issue as R2. Okay, basic settings, interfaces including loopback interface, static routing. Okay, in my case this is only gigabit 00, and here gigabit 10. Okay, and copy this. But start R2. Configure terminal to access global configuration mode. Okay, then copy this. Here, right click to paste. Okay, no issues, no errors. R3. Router R3. Hostname, basic settings, here gigabit 00, and here gigabit 10 in my case. Default static route and OSPF. Very good. Start. Okay, access global configuration mode, configure terminal, and copy this. Right click to paste. Very nice. Switch D1. Basic settings, interfaces, layer 3 interfaces. In my case, this is Ethernet 1.1, and here is Ethernet 2.3. Okay, Ethernet 2.3, loopback interfaces, IP routing, and OSPF configuration. And shut down any other ports. Okay, if E1 and 2.3 in use, shut down. Okay, shut down from E00 to 03, E10, E11 in use, E1, 2 to 3, E20 to 3, and no, E20 to 2, 2.3 in use, E30 to 3.3. Okay, start the device. Configure terminal. Select all this, copy, and right click to paste here. Very good, no issues. Very nice. Switch D3. Okay, basic settings, interfaces. Here for me is Ethernet 1.1. Here Ethernet 2.3. Loopbacks from 16 to 23. IP routing and OSPF configuration. But this range is the same range of the D1 switch to shut down all unused ports. This range in my case. Start the device. Configure terminal and copy all this to D3. Copy, right click to paste. Okay. No issues. Very good. Configure PC1 and PC3 with IP addressing. Use these addresses. Okay, before to do that, in my case, I'm using VirtualBox virtual machines and review the network, generic driver, UDP tunnel, and cable connected. The another machine, the network. Generic driver, UDP tunnel, cable connected. Okay. Start this device. Edit, wired, IPv4. Okay, address 10, 10, 1, 10, 24, and gateway 10, 10, 1, 1. Okay, save. Close this and start networking. PC3, start. IP address, edit, wired, IPv4. 10, 10, 10, 10, 5, 10, 24, and 10, 10, 5, 1. Save, close this, start networking. On PC1, verify end-to-end connectivity from PC1 ping PC3, 10, 10, 5, 10. This is PC1, ping from PC1 to PC3, 10, 10, 5, 10. Success. Ctrl-C to stop. Use traceroute. Six hops. 1, D1, 2, R2, 3, R2, 4, R3, 5, D3, and 6, PC3. Very nice. From PC1, ping the first loopback D3, 10, 10, 16, 1. 10, 10, 16, 1. Success. Okay, this is the trace route. Success and ping. Ping. Success. Ctrl-C to stop. 5 hops. Okay, from PC1 to D3, 10, 10, 16, 1. 1, 2, 3, 4, 5 hops. For PC1, ping the default gateway loopback on R2, 209.165.200.225. This Internet 225 loopback interface on R2 from PC1 and should have 1, 2, 3 hops. Ping to omni 165, 200, 225. Success. Control C to stop and trace route. Trace route. Trace route. 3 hops. Verify the routing table on R1 and R3. Show IP route, OSPF. Begin gateway. R1. Okay, you can see before to do that, you can see this message. Duplex mismatch on Ethernet 1.1. Okay, duplex mismatch. This is Ethernet 1.1. Okay, go to D1. Okay, Ethernet 1.1, not full duplex. Okay, configure on D1 on layer 3 switch Ethernet 1.1 to full duplex. Interface Ethernet 1.1. Duplex full. Exit. The same way on Ethernet 1.1 on D3. Ethernet 1.1. Okay, interface Ethernet 1.1. Duplex full. Very good. Exit. Okay. Now show IP route OSPF begin gateway on R1. Do show IP route begin gateway. You will see the static default route, the directly connected network 10.10.0.0 and directly connected network 64.100.0.0. This 10.10.0.0 and 64.100.0.0 on R1. And 3 OSPF neighbors 10.10.1, 2, and 3. Okay, 10.10.1, 2, 3, and this is 1. Okay. Very good. The routing table of R1 only contains the local OSPF routes. The routing table confirms that R1 has knowledge of the networks connected to D1. Notice, however, that R1 has no knowledge of the routes connected to R3 OSPF domain. The reason why PC1 can still reach PC3 is because R1 has a default static route to R2. R1 forwarded the traffic to R2 because it did not know where the 10.10.50 network was. R2 has a static route to this network and therefore forwarded to R3. R3 exit, show IP route OSPF begin gateway. Okay, and you will see the OSPF networks 5 and from 16 to 23. Okay, 5 is this, and from 16 to 23 here. Okay, but if you will use only show IP route OSPF begin gateway, You will see the static default route, directly connected network 40, this 40 and 64.100.10, 64.100.10. Configure GRE over IPsec using a crypto map on R1. A limitation of IPsec VPNs is that it only forwards unicast traffic across the VPN tunnel. Therefore, routing protocol traffic is not propagated across the VPN tunnel. What if the network policy was to enable the OSPF routing protocol to operate over the IPsec VPN tunnel? This could be accomplished by configuring GRE over IPsec VPN. There are two methods to configure GRE over IPsec. Crypto maps. This is an older classic method of configuring GRE over IPsec tunnel in IPsec profiles. This is a newer and simpler method of configure GRE over IPsec. Crypto maps and IPsec profile configuration options are compatible with each other. Although tunnel IPsec profiles is now the preferred method to configure GRE over IPsec, crypto maps are still widely deployed and should be understood. Okay, on R1, configure the ISIKMP policy and pre-shared key. Like site-to-site VPNs using crypto maps, GRE over IPsec also requires an ISIKMP policy configuration and pre-shared key configured. Okay, policy sequence number 10, and all these parameters on R1. Crypto ISIKMP policy sequence 10. Encryption, AES to 56 bits. Hash SHA to 56 bits. Authentication pre-share key. Diffie-Hellman group 14. Lifetime 3600, 3600, 3600, 1 hour. Then exit. Pre-shared key Cisco 123 on R1. This command points the remote peer gigabit 00 IP address on R3. Okay, if this is the source, the destination is R3 and we'll use gigabit 00 IP address and it's 64.100.1.2. 64.100.1.2. Crypto ISIKMP, the key is Cisco 123 address, the another peer 64.100.1.2, enter. Configure the transform set and VPN access list. Create a transform set called GRE-VPN using AES-256 cipher and ESP and the SHA-256 hash function. Okay, this is the transform set. Crypto IPsec transform set. The name GRE-VPN case sensitive. ESP use AES 256 bits. ESP SHA 256 HMAC. Enter. Unlike a site-to-site IPsec VPN, the transform modes use transform modes. The mode command is used to identify the type of tunnel that will be established. The default is tunnel mode. However, GRE over IPsec should be configured using the mode transport commands. Mode transport. Exit. Now create the access list, call it GRE VPN access list that makes the tunnel interface traffic interesting. IP access list extended GRE VPN ACL permit GRE protocol from host the source 64.100.02. This is the source 64.100.02 R1. And the destination is the another side, the another peer 64.100.12. 64.100.12. Enter. Exit. Configure the crypto map and apply it to an interface. The name GRE-CMAP and associates the new GRE VPN access list. Transform set and peer. Now create the map. Crypto map GRE-CMAP. Number 10 IPsec ISAKMP. Enter. Don't worry about this message, only continue match the address on this access list, GRE VPN access list, GRE VPN access list. The transform set, this transform set, GRE VPN, transform dash set GRE dash VPN. Okay, set transform set space transform set. Very good. And finally, the peer, the destination peer 64.100.12. Set peer 64.100.12. Exit. Assign crypto map called GRE-map on gigabit 00. Okay, this case should be GRE-CMAP. Okay, this map GRE-CMAP on interface gigabit 00. The exit interface is this gigabit 00 in my case on R1. So configure on gigabit 00. Interface gigabit 00. Crypto map GRE CMAP. Okay, CMAP. Enter. Exit. ISAKMP is on. Very good. Now configure the GRE tunnel interface. To enable GRE on the tunnel interface, the tunnel mode GRE IPv4 command is required. However, this command is enabled by default and will therefore not be configured in our example. Okay, configure the tunnel. Here, this pink connection is the tunnel. Tunnel 1 is a virtual interface on R1 and will have the IP address 172.16.1.1. Subnet mask theory. Interface tunnel 1. Set the bandwidth. Bandwidth for 4,000 kilobits per second is 4 megabits per second. IP address 172.16.1.1. Subnet mask theory 252. IP MTU 1400. Tunnel source. Tunnel source is this 64.100.02. 64.100.02. 64.100.02. And tunnel destination 64.100.12. Okay, the destination on R3 64.100.12. Enter and To support IPv6 traffic, configure the tunnel mode GRE IPv6 command. Very simple. Now configure GRE over IPsec using a tunnel IPsec profile on R3. You will configure R3 to support GRE over IPsec, although we could configure R3 to also use crypto maps. We will instead configure GRE over IPsec using IPsec profiles to demonstrate how both methods are compatible with each other. This means that a router configured with GRE over IPsec using crypto maps can communicate with GRE over IPsec using tunnel IPsec profiles. A tunnel IPsec profile requires fewer commands than the cryptomap method. However, it still requires an ISA-KMP policy configuration, pre-shared key, and transform set to be configured. It will then still require a tunnel interface to be created. Okay, configure the parameters for ISA-KMP policy on R3. Configure terminal crypto ISA-KMP policy sequence time encryption AES to 56 bits. Okay, sorry, 256 bits. Okay, then hash SHA 256. Authentication pre-share under Diffie-Hellman group 14 and lifetime 3,600 seconds, 1 hour, then exit. Okay, the same parameters configured on R1. Same parameters configured on R1. Transform set crypto ISA-KMP key, same password as R1, Cisco123. Okay. And the peer address, now the destination is 64.100.02. This 64.100.02. If R3 is the source, R1 is the destination, and the peer is 64.100.02. Now the transform set crypto IPsec transform dash set GRE dash VPN. This is the name of the transform set. Use the same parameters as R1, ESP, SHA, space 256, ESP, SHA 256, HMAC. Okay, it's ESP AES. Okay, crypto IPsec transform set, the name GRE-VPN, ESP AES, 256 bits, ESP SHA 256 HMAC. The same configuration as R1. Set the mode transport, exit. Configure IPsec profile. Instead of cryptomap, we will configure an IPsec profile called GRE profile using the crypto IPsec profile. Okay, create the profile GRE-profile. Crypto IPsec profile, the name GRE-profile. IPsec profile configuration mode specify the transform set to be negotiated using the set transform set command. Multiple transform set can be specified in order of priority. The first transform set name specified is the highest priority. Okay. this transform set GRE-VPN. Set transform-set the name GRE-VPN, case sensitive. Then exit. Now configure the tunnel. Okay, this tunnel 1, IP address 172.16.1.2, subnet mask 30 on gigabit. Interface tunnel 1 bandwidth 4000 kilobits per second, 4 megabits per second. IP address 172.16.1.2, 255, 255, 255, 252. IP MTU 1400. Tunnel source. Okay, the source is R3 64.100.1.2. 64.100.1.2. And the destination 64.100.02. Tunnel destination 64.100.02. Okay, exit. Apply the IPsec profile, GRE-profile to tunnel 1. Okay, tunnel protection, IPsec profile, GRE-profile. This profile, GRE-profile. Enter. Okay, should be placed on tunnel 1 interface. Don't forget that. Interface, tunnel 1. And tunnel protection, IPsec profile, GRE profile. Very good. ISA KMP is on. Exit. On R1, perform an extended ping to R3, 10.10.16.1. But the source should be 10.10.01. 10.10.01. Okay. From R1, ping D3, 10.10.16.1. But the source will be gigabit 10, 10.10.01. Ping 10.10.16.1. But the source 10.10.01. Success. The pings are successful, and it appears that the VPN is operational. On R1, verify the IPsec SA encrypted and decrypted statistics. Okay, on R1, show crypto IPsec SA, include encrypt, decrypt. Okay, packets encapsulated 0, decapsulated 0, encrypted 0, decrypted 0. No packets were encrypted. Okay, from D1, trace the path taken to R3, 10.10.16.1. Okay, go to D1, exit, and trace route, 10.10.16.1. Okay, 4 hops, very good. from D1 traceroute to D3 10.10.16.1 1, 2, 3, 4 hops. Okay, this connection is not using the tunnel. Okay, 4 hops. The packet sent by D1 takes the route R1, R2, R3, and D3 path. 4 hops. Okay, these 4 hops. It does not use the GRE over IPsec VPN. The reason for this is because the VPN access list has been altered to make GRE traffic interesting. Therefore, we must generate traffic that will use the tunnel interface. To do so, we will configure the OSPF routing protocol to enable OSPF on the tunnel interface. Okay, remember the access list configured on R1 Okay, remember the interesting traffic was configured connection from 64.100.02 to 64.100.12. Okay, from 64.100.02 to 64.100.12. Configure OSPF to advertise the tunnel interfaces. Okay, router OSPF notify the tunnel subnet on R1 and also on R3 on OSPF process notify the tunnel subnet. This 172.16.10 subnet, this network. Okay, configure terminal router OSPF 123 network 172.16.10 wildcard for 30 is 3 area 0. Exit and go to R3 router OSPF 123 network 172.16.10 wildcard 3 area 0. Enter and wait a moment, and this is the neighbor adjacency between R3 and R1 using the tunnel. Okay, between R1 and R3, the adjacency. Verify the GRE over IPsec tunnel on R1 and R3. On R1, show interfaces tunnel 1. Do show interfaces tunnel 1. Okay, you will see tunnel 1 is up, protocol up. The address is 1. Encapsulation is tunnel protocol, transport, GRE IPv4. On R3, show interface tunnel 1 and include all these options. R3, do show interface tunnel 1 pipe. Include is up. Internet address. ENC tunnel protocol. Enter. Okay. Tunnel is up, protocol up, internet address 2, encapsulation tunnel, protocol and transport GRE IPv4. show crypto session on R1. Do show crypto session. You will see the remote peer 1.2, the port for IPsec 500, okay, IKE version 1 SA, the local 02, the remote 1.2, port 500, IPsec, the interesting traffic configured on the access list. Okay, and it's configured on gigabit 00, the exit interface to internet. R3. Okay, do show crypto session. Okay, this is not configured on physical interface, it's configured on tunnel because it's configured with profile, session active, the remote peer 02 port 500, IKE, the local 12, the remote 02, the interesting traffic from 12 to 02. Remember, when you configure profile for GRE tunnel, an access list was not configured, but interesting traffic was defined when you configure the tunnel, the source and destination in the tunnel. Okay. On R1 and R3, verify OSPF routing. R1, do show IP OSPF interface brief. Okay, interface is tunnel and gigabit 10. Okay, tunnel and gigabit 10. Tunnel and gigabit 10. Configured, included on OSPF. For R3, do show IP OSPF interface brief. Tunnel and gigabit 10. Tunnel and gigabit 10 included on OSPF. Show IP OSPF network. Do show IP OSPF network. Okay, this is R3 and this is D1. Okay, the networks for R1 in OSPF, R3 and D1. R3, do show IP OSPF network. Okay, this is R1 and this is D3. For R3 neighbors, R1 and D3. On R1, show IP route OSPF, begin gateway. Do show IP route OSPF, begin gateway. And you can see, you will see the local OSPF routes 1, 2, and 3. Okay, 1, 2, and 3. But now you can see the 4, 5, and from 16 to 23 on the another side. on the remote side. Okay, 4, 5, and from 16 to 23 on R3 the same way. Do show IP route OSPF begin gateway enter. Okay, OSPF. Okay, you can see your local OSPF routes 5, 16 to 23, 5, 16 to 23. But you can also reach to 0, 1, 2, and 3 on the remote side. Okay, 0, 1, 2, and 3 on the remote side. Okay, on R1 verify, do show IP route, how to reach 172.16.0.0. It's a directly connected network. Verify that there is an operational logical point-to-point link between R1 and R3 using the GRE tunnel interface. Okay, use tunnel. It's a directly connected network on R1. Okay, for R1, 172.16.0.0 or 10 is a directly connected network. So that's why I use C for connected. Directly connected network, the same way on R3. Do show IP route 172.16.0.0. Okay, it's a directly connected network and uses the tunnel interface. Okay, from D1 test trace route to 10.10.16.1. From D1 trace route to D3. R1. Okay. From D1 trace the path taken to R3 10.10.16.1. Okay. From D1 trace 10.10.16.1. Trace route. From D1 trace route 10.10.16.1. Only 3 hops. Before configure tunnel, 4 hops. After, then 3 hops. Okay, 1 hop, 2, and 3. Okay, using the virtual tunnel. Also, you can try ping. Okay, very good. And verify on R1, show crypto IPsec assay. Include encrypt decrypt. Show crypto IPsec assay. Include encrypt decrypt. Okay, now packets encapsulated 114, decapsulated 110, encrypt 114, decrypt 110. Very good. And also you can from PC1 ping 10.10.16.1. Okay, this is Control Shift stop. This is D3 trace route. Okay, 4 hops. Before the tunnel were 5 hops, but now 4 hops. Okay, from PC1 to D3 trace 1, 2, 3, only 4 hops. And now ping the another PC 10 510 ping. Success, Control-C to stop and trace route. Only 5 hops. Before 6 hops. Now 5 hops. 1, 2, 3, 4, and 5. Thank you.